Now we move on to the truck structure design for a railroad. So basically, we talk about truck. We're talking about the railroad where the train passes through. So actually, the truck system composed of components to make it as a truck wherein the train will pass through as it travel from one point to the other. So basically, for our design standard for contemporary light rail transit, or the LRT truck structures, whether in an upgrade, aerial, or tunnel environment, it differs considerably from principles of either heavy rail transit or railroad service. So basically, there is the design standard for a truck structure is dependent on the grade, the aerial, or the tunnel where our truck will be designed. So they have different principles to be considered from heavy rail transit or railroad services. So basically, for our LRT system, can be constructed which result in horizontal and vertical truck geometry that can often affect the light rail vehicle or the design and performance. So you have to take note that if you are a light LRT designer, you have to consider not only the truck geometry but also the design characteristic of the LRV or the light rail vehicle and how it will respond to the guideway geometry. So actually this is particularly true in embedded track located in street. So in general, actually the construction of LRT guideway in a city street constitute the greatest challenge to the light rail track designer. For the design of a truck, so during the truck design, the most critical or the most crucial activity is getting the correct dimension that will be used for the truck gauge and wheel gauge and for the width of the flangeways through a special truck work. So for a vehicle truck factor, so in general, you have to take note that we have to reduce in the reduction of the lateral clearance between the wheel flange and the rail head gauge face, either through increasing the wheel gauge preferred or decreasing the truck gauge, improves wheel tracking of the rail in curves by keeping the truck wheel as square to the rails as possible. So you have to take note. So when we speak of flangeways, though in a truck system, so flangeways actually is the flanges. It is if the ways or the flanges where the wheel of the train passes through. So that is a flangeway. So flangeway are the flanges of the wheel that passes through. On the other hand, wheel gauges actually is the distance between two wheels on the same axle of a vehicle. So for a vehicle shock factor, in general, as mentioned, the reduction of the lateral clearance between the wheel flange and rail head gauge face, either through increasing the wheel gauge, which is preferred, or decreasing the truck gauge, which improves wheel tracking of the rail in curves by keeping the truck or the wheel as square to the rails as possible. So this reduces hunting, skewing, and flange attack angle and results in improved performance through curved track and special track work. So the truck that is nominally constructed to standard gauge can actually be tighter or wider than 56.5 inches, depending on a variety of circumstances. So the truck gauge can be adjusted along the route so as to optimize vehicle-to-truck interactions. So the condition that can require gauge adjustment include, so basically for the gauge, there will be some adjustments, and those adjustments this may include on the curvature, the presence of lock or curve restraining rails, and several vehicle design factors. So the vehicle factors actually include the wheel diameter, the wheel tread taper, and with the wheel flange shape, including both height and thickness. So the distance between the axle and the wheel gauge the distance between wheels mounted on a common axle. So we have here the illustration showing to us the narrow flange wheel, wherein this would be the design, which includes the dimensions, the standard dimensions for a narrow flange wheel. So for a curved truck gauge, we have to take note that for the truck gauge and flange weight dimension in a curved truck, so it must be determined analytically for each combination of the vehicle factors. So there are some graphical methods for analyzing the issue. So basically, we have here an illustration showing to us the diagram for determining a flange weight width by Filkin-Wharton diagram and by Filkins-Wharton plot to establish the flange wage. So this one is illustration for the wheel section for Nitram plot, the oblique view. So this one is a wheel section for Nitram plot. So these are some of the illustration for the wheel section of a train. So we have to take note that rail cant is a significant factor. It is an important factor in wheel-to-race interface. So which means that you have to take note that the wheel is in contact with the rail. When we talk about rail, if you have the track system, if you're going to observe on our MRT or LRT, the track system, there is a parallel steel bar, or it can either be a steel, it can be a wooden or concrete. That parallel component of the track system is what we call the rail. So there must be a good or harmonious relationship somehow. There must be a good interface between the rail and the wheel. So it is an important factor to have a good wheel to rail interface. You have to take note that Kant describes the rotation of the rail head toward the track center line. It is intended to complement conical wheel treads in promoting self-steering of wheel sets through curves. So the Kant also moves the vertical wheel loading away from the gauge corner of the rail and towards the center of the ball of the rail head. Of course, Kant, we're talking about the super elevation. So there must be a good design for the rail cant. So or the rail cant or the super elevation, if we're trying now to have the design section for a curve on the track system. So these are some of the illustrations showing to us the rail cant design and wheel contact. So we have here the ratio of the super elevation or the cant between the rail to wheel contact. So for the most precisely calculated standard for truck gauge and flange weights will be of no value if the track is not constructed and maintained in a manner that ensures that the design intent is achieved in practice. So obviously, we have to take note that constructed and maintained tracks are not possible, and the cost of achieving such perfection would probably exceed the value of the benefit that would ensue. So basically, it's very important that in the construction of a railway, there must be a good maintenance so that it will ensure the long lifespan of the structure. So we have here a tabulation for track construction tolerances. So tolerances actually should be specified that it should protect. Actually, tolerance should be specified wherein it should protect the design objective as closely as possible and are practical and achievable with the materials and equipment available. So we have here the specific type of truck, then we have the construction tolerances for each and location tolerances for each type of truck. We have to take note that the restraining rail are installed inside the gauge line of the curved slow rail to provide a uniform flangeway. So the restraining rail provides additional wheel steering action using the back face of the flange of the wheel that is riding on the inside rail of the curve. As mentioned a while ago, there is an interaction or an interface between the wheel and the rail. So which means that we must have the rail design must be fitted to the design of the wheel of the train. So we also have this what we call double guard. So double guarding extremely on sharp curve wherein we place a restraining rail adjacent to the high rail as well as to the low rail. So that is basically double guarding. So we place a restraining rail which is adjacent to the high rail as well as to the low rail. So this idea of double guarding is installed, which are designed to counter the tendency of the second axle on a truck to drift towards the low rail. So basically, it's for the safety and comfortability of the train itself. So for the working phase of a restraining rail on the inside of a curve, it tends to assume an angle to the vertical as it wears. So because this is basically it is leading edge of the wheel and it contacts the restraining rail and it is non-tangential to the rail. And you have to take note that basically the potential problem here is the time by the time the working phases reach the optimum angle, the wear may have widened the flangeway. So in terms of the restraining rail design, also project above the plane of the rail of the running rail. So we have to take note that the guards on the girder guard rail were 1/4 to 3/4 inches above the top of the rail. So there are instances wherein the separate restraining rail are as much as an inch above the running rails. So it is an important subject one of the important subject is the track modulus. So this is actually used for complex mathematical calculations to analyze ballasted track as a structure. So basically for our track system, we have a ballast. So the ballast actually it's somehow composed of those are it is a formation of the track bed. The track ballast is a formation of the track bed upon which the railroad ties are being laid. So basically it is packed between and below and around the ties. So it is used to bear the load from the railroad ties to facilitate drainage of water and also to keep down vegetation that might interfere within the track structure. So that is the track bed of our track system. So we have here illustration for a two standard design for track structure on ballasted truck. We have the timber cross tie and we have the concrete cross tie. So these are illustration for ballasted double tangent and single guarded curve truck. So this is a concrete cross tie and both the single guarded and the double guarded are concrete cross tie. So for the design of ballasted truck, so these are some of the consideration. We have to consider the rail section, the track gauge, the guarding of curved tracks, and restraining rail features, the rail fastening and tie plates, and of course the track cross ties and corresponding track structure to suit for the operations. So this is a figure showing to us the components of a track system. So we have the sleeper, we have the weld, this is the rail, you have the ballast, this is the ballast and the fastening. So basically if you're going to observe, ballast is the roadbed, so it is somehow a formation of a rock stone like so roadbed. So we have this is the illustration for and the components of a track system.